So let me give a recap of the course that we have done so far. We have started with the large language models, and in particular, the transformers. We started with a use case, namely that of semantic search. We create sentence embeddings. The sentence embeddings helps you create use cases like semantic search. That is one use case. Today, I'll extend the amount of use cases that we will do with the sentence embeddings. Right? Now, given the fact that we can do sentence embeddings and hybridize that with a k-nearest neighbor or approximate k-nearest neighbor, we get a pretty powerful search engine. Then you hybridize that with a large language model. And what you get is retrieval-augmented generation. The reasoning is as follows. Suppose you have a question. You take that question into your document pool, you search through it, you get the search results. Once you get the search results, you give it to the large language model to interpret it for you in the context of your question. And so you get an answer which is more relevant. So in a way, you can think of RAG as a natural evolution of search, whether it is enterprise search or it is web search. So you see companies like Perplexity, for example, give you the ability. They treat the entire web as a search repository. They search into that, they get back the search results, and then applying an LLM means you don't have to scroll through the search results one by one and see which one is relevant. The large language model does that for you. That's a great way of evolving a search engine into a RAG. Are we together? We could have looked at this problem the other way around and said that LLMs, just large language models inherently, have a host of problems. They hallucinate. They make things up. Why? Because they are plausibility engines, right? They will give a very plausible answer. It is very, very hard to make or force a large language model to always be truthful. It will try to give you the most plausible answer instead. Likewise, a large language model is inherently dated. It's very, very expensive to train a large language model. When you burn, like for example, to train Llama 3.1 billion parameter, the 405 billion parameter model, it cost Meta, Facebook, from what I understand, 24,000 or 25,000 GPUs. It ran through 1.3 million tokens, and it ran for practically, I don't remember what the number was, but an insanely large number of GPU hours and flops, floating point operations of petaflops that it ran through. So that's what it takes to train a large language model, which means that you cannot have a large language model trained every single day, right? The companies train it, they release it. But when they train it, what happens is inherently it becomes dated because it can only be trained with data up to the point. Once a model is released, knowledgeable information. Yeah, go ahead, Pawan.
When you said tokens, right? You mentioned that it took 1.3 million tokens. So, like, what does the token mean in that context?
See, one simple way to think about tokens in the natural language space, a very rough way of mapping it is just to say a word. Cat, for example, is a token. Right? Dog is a token. Any word is a token. Now, let's look into it a little bit more. If I have a statement, the cow jumped over the moon, you might say the cow jumped over the moon, and the full stop, the punctuation, they are all tokens. Now, what happens in reality is, in language, words have various declensions. For example, the word jump, jumped, jumping, right? Likewise, the word run, ran, right? Sit, sat, running, sitting, they all have a fairly similar root or connotation. It's just the tense or the action associated with it. So what people do, or for example, the word, some word, employed, and then you have unemployed, right? Undone, and so forth. So prefixes like un, they have a meaning. They negate the whatever follows after that, isn't it? And likewise, running, sitting, jumping, they all have a ing suffix, right? That implies that particular action happening now, or something like that. So what really you do is that you don't treat word as tokens, but you treat word pieces as tokens. For example, jump is a word piece, and ing, the suffix, is a word piece. That suffix can be applied to many, many words. And it leads to reduced vocabulary. Then you don't have to have the ing, jumping, running, etc., etc., all of them as unique words. Jump is enough, and ing is enough, and that ing can be the suffix for many words. So the technical term is word pieces. So a token in natural language maps to word pieces. Are we together, Pawan?
Yes, Asif, thank you. So it kind of brings, it gets me reminded of something you mentioned earlier, that the recent large learning models, they ingest so much data, and we said that we are running out of words, right? Like you mentioned the tunes of like billions or something like that.
Yes.
So
go ahead.
So in that case, when we hear that Meta only used like 1.3 million tokens, so does that mean it did not use all the, like, that it did not train it well enough?
No, 1.3 trillion tokens with a T.
Okay, yeah, thank you. I noted it down as million, so thanks.
1.3 trillion tokens. That's a vast number of tokens. Actually, 1.3 trillion tokens exceeds all the text available in the world publicly. So what they had to do is they had to generate some data to train this model. They had to generate new text to train the model.
Is it across all languages?
It is across, all languages. In fact, major languages. See, now that's a very good discussion. When we train these large language models, how do we do that? Generally, these large language models are trained across most languages. The reality becomes there are languages that are what are called resource poor. Right. So, for example, look on the web for Nepali text, or Bhutanese text, or things like that, and you will find that there isn't that much literature available. Whatever is available is scraped and taken. And one of the great achievements of large language models has been exactly that. They become very good translators because they are very good language translators. Now, what can you do? You can translate the vast amount of valuable knowledge, like Wikipedias and everything, and bodies of knowledge from one language to another. And you can therefore go and enrich the resource-poor languages. One second. And as you're aware, Indian government actually at this moment, and I'm sure the government of many, many countries are putting in a concerted effort to translate a lot of knowledge that exists into what are relatively resource-poor languages. Right? India is teeming with languages, and this is really a worthwhile effort. So you can directly see how when we think of large language models, people a cliche onto the chatbot. Actually, it's not. It has the far-reaching impact you can see when you see how well it is helping people who are in resource-poor languages, and how well they can communicate now thanks to these initiatives. Equally well find information, find knowledge on the internet, right? Or use these large language models to harvest all of that knowledge. Girish.
So with Llama 3, 1.3 trillion tokens translates to how many parameters?
Tokens that is data that has nothing to do with parameters. Remember, you can take a model. Model is made up of weights and biases, right? These tokens are input data. You can take the tiniest model and feed trillions of data points through it. The two are independent of each other, right? Generally, what happens, I mean, not completely independent, but that's not the way you should think. Remember, you take any model, let's say you take random forest, and you're training a classifier on it. How many data points, what's the size of your data set has nothing to do with how many trees you have grown in your forest, isn't it? So, or a very simple thing, if you're doing a linear regression model, it has just two parameters, let's say in one dimension, right? Beta naught, beta 1, right? Now, how many data points, XY, tuples you train that model with has nothing to do with the fact that the model still has only two parameters. All you're doing is you're finding the best possible value for those two parameters, isn't it? So data is what you train the model with. Data is what helps find the best value of the parameters of the model. Is that clear? Not yet. You really should come to the Thursday class, the Intro to AI, because we talk about these things from the ground up. I apologize. This is a very applied boot camp kind of a workshop. So we are very practically motivated. But I would be happy to sit with you. I mean, and explain it offline, but let's move on with the course. I'll do that.
Just for everybody's benefit, I posted a video from Andre, the 2-hour tokenization video. So I think it'll benefit everybody to kind of watch that. That's one. The second thing is, if you wouldn't mind, seems to be some confusion, maybe 10 minutes just to, whiteboard how the tokenization kind of works. That's probably going to clear up some minds.
Okay, I will do that. How about this? Give me a moment. Let me at least do the review of what we have done so far, and then I'll come to that. Just a few more minutes. Go ahead. Turn on your microphone so everybody. Yeah.
So one thing as to add up when you said on the Indian government, was trying to
Yeah. See, one thing. If the voice isn't coming loud, it means nobody is hearing you. Yeah, nice. Yes.
Yeah. So I was reading for where Google India DeepMind director was talking about the same project is there. And one fact was that in India we have so many languages where there is no written script. And you were saying that they are building the same purpose even for those languages, like close to 516 languages.
Right.
How is that?
How is that possible?
Yeah.
How is it? So the question, I'll just restate. We have a question here in the audience saying, in India, there's an initiative to create or this AI generated or LLM capabilities for languages which don't have a written script. How is that possible? Would somebody like to enlighten us?
Audio.
How with audio? No, that's right. See, you give the answer, but I'll dig a little bit deeper. See, guys, for most of humanity, our knowledge has been an oral tradition, right? It has been passed from person to person through stories, through narratives. But you see the proliferation of mythologies in every culture. Interesting stories. Why do you tell interesting stories in every culture? Exciting, thrilling stories. The gods and the demons fighting, good and evil and all of that. Because they form a great medium to embed whatever it is that you want to pass down to the next generation. Right? So much of human knowledge, much of human culture, much of human philosophy has been oral tradition passed down. The written language is actually a much more, a very recent invention. I would say just a few thousand years ago, when people started writing on various leaves, right? And on papyrus and so on and so forth. So, and obviously it was also limited to the elites in most civilizations. There were the people who were allowed to see what was written on the scrolls, the papyrus, the palm leaves and whatever. And for other people, they would be beaten to death if they so much as looked at it. Right? So never forget that. We never get fixated on the fact of the written word. Human knowledge is to a large extent an oral tradition. Much of what your mind picks up generally before you utter your first word, which is about the age of 2. And so, obviously, and I'm bringing it up because this is a very active area of debate amongst research communities and linguistics and so on and so forth. And so people are applying AI to capture not just oral traditions, oral languages which have no written form. Oral languages that have no written form transcend human languages. Today, for the first time, because of AI, because of these transformers, because of these things, we are beginning to understand exactly what the whales are up to, what the birds, what the things are up to. Right? Those of you who are in the Tuesday class, and I mourn for you who are not, but those of you who are in the Tuesday class know that one of the homeworks we have given you is literally to recognize the chirping of the birds and the barking of the dogs. Right? So dogs have barked and birds have chirped, and they have had a pretty healthy communication. They have expressed their emotion, their fears, their everything, without ever bothering to. When was the last time you saw a dog all of a sudden taking its paw and writing on the wall? Right? They don't do that. That's not how they communicate. So this is one of the big achievements of AI, that we are for the first time transcending beyond written languages. A lot of effort is going into it. Right? And the more we do that, the more we realize that actually, for example, for the longest time, people believed that whales communicate using some primitive vocabulary. Right? Here's danger, here's food, things like that. Now we are realizing that their language is about as complex as human language. Never forget the fact that they have far bigger brains. Right? So a lot of interesting discoveries are happening, and this is true of it. If you look at the Eurocentric point of view, civilizations that didn't have written language were always looked down upon as basically undeveloped and primitive. Macaulay, the Brit under the British rule in India, for example, made a famous statement when he was asked to come and study the literature, the philosophy, the things of India, to determine whether it should be included in the colonial Indian school curriculum. Famously wrote that all of India and Asia's, by the way, Asia, all of Asia's knowledge across thousands of years will not be able to stand up to what is a fifth grader's library in Great Britain. Right? So you can imagine how now that looks utterly racist and colonial today, right? And you might even turn around and ask, who really cares about what a tiny island with the Atlantic thought about us 200 years ago, right? They'll be soon forgotten. But we do the same thing in India. Cultures that don't have written tradition, they are always economically deprived, marginalized, demeaned. Their traditions are devalued. And there is a cultural imposition, just as the Brits imposed upon our culture. Look at it. There's a cultural imposition on the. I say it as a person coming from Northeast frontier and those regions, Nepali and part of that. So I'm very sensitive to these issues. Sometimes people who, well, I more or less look Indian, but people who look less, who are from the hills, they come to, in India, to the Taj Mahal or the Qutub Minar or any of the things. There are two lines, one for foreigners, one's for Indians. Foreigners, of course, pay more. And the police often pushes them into the foreigners line and says, you're not Indian. It happens very frequently. Anyway, giving you a perspective on how, in a way, AI is transforming that sort of outlook. It is helping us create a more even society. See, AI will do a lot of harm. There's no doubt about that, right? It will do as much harm as it will do good, like any other technology. But if you look at the good that it's doing, these are some of the good it's doing. Right? And for the first time, we are understanding, because we are talking about large language models, a good point to bring up. For the first time, we are understanding that animals genuinely, we have evidence, have complex emotions and complex languages of their own. Well, That, yeah.
Just a quick question around the LLM fine tuning. Right? Is there a threshold of the data which you need to fine tune the model?
Mhm.
Because there is always a distinction, at least in the corporate world, right? That if you don't have enough, you may not be able to fine tune, or you may need a rack, maybe not very foundational.
This is a good question. The question is, how much data is enough for fine-tuning? And should we just stick with that? So I would answer this question differently. Your first rule should be, it's part of the philosophy of transfer learning. Because a foundational model has been pre-trained, you have to ask yourself, can I get away just using the model as is? Because if you use a model as is, so here's okay, maybe this merits a little bit of writing. Is my screen shared, guys?
No.
No,
No,
it
not
is not yet. So let me explain this.
no.
Yeah, no, it is. Thank you, Kate. So here is the hierarchy. Think of a model. You have a model. Let me make the fonts bigger. Model M. It has certain number of it has weights and biases, right? Lots of weights and biases. Now, what happens is that when you have three modes. The model could be in training mode, or it could be in inference mode. And there is, of course, a validation mode. Which is considered a part of training these days. Right? So what you do is, let's take the very basic. You're trying to fit a straight line to data, linear regression. What would you do? You would go get data, training data. You would have test data. You would do some, well,
Change the background.
oh, I should change the background. Okay. Sorry. Let me do that. Draw, insert, background, view, page color. Oh, I'll have to start all over. Okay. Or let me see. Another page color might do, just for the time being.
Just go with dark black, sir.
Okay, yeah.
Yeah, this is,
Yeah. Okay, so you have training data. You split your data into training and test. You would take, your model is beta naught plus beta 1x. Let's say a model, y hat is equal to this. What do? You train the model over and over again. And then once it is trained, you test it. You see what is your MSE, for example, or some other metric, MAE, whatever it is that you want to take it. Pick your measure. You would say, okay, now R squared, pick your measure. You say that my model looks good, my metric looks good. At that moment, your model goes into pure inference. Now, look at this. While you're training it, right? How do you train it? You not only need to know, at any given moment, you're not only storing the values of beta naught, beta 1, you're also storing the values of gradient L, right? That is beta naught, beta 1. So you're storing at least twice the number of parameters, isn't it? The twice the number of variables. If the number of parameters here is 2, you at the training time, you have 4 things to manage, to keep track of. Am I making sense, guys? Right now, what happens in a neural network, it is very similar. You have lots of weights and biases. In the Lth layer, there'll be some weight I, right, coming from a node I to node J, and so on and so forth. Lots and lots of weights. You have the same problem. During training, you have to do, then you have to keep track of IJL, the derivative, partial derivative. You also have to keep track of the quadratic term. Because if you use something called an optimizer, there is something that you use during training to do gradient descent, to train the model. It's called the optimizer. optimizer. Basically, it helps you do something called a gradient descent. A gradient descent is the heart of learning, right? So what it in reality means is that for every variable, you multiply it by 3x, right, during training. And then to bring in some overhead, you multiply it by 1.2. So a very good rough rule of thumb is 3.5x is the amount of space needed, right? Now the problem we are facing, Ravinder, is that these large language models, they're so ginormous, they barely fit into our hardware. So let's take a 7 billion parameter model, which is considered a small model. 7 billion parameter model, right? It has 7 billion parameters. Now, if you use just basic quantization, let us say that you use 16-bit, because these things are trained at 32 bits. Now, it means a floating point, because these numbers are what? Floating point numbers? Weights are floats, right? In other words, they're decimals. They typically contain 4 byte of information, right? That's 32-bit. That's what they're trained on. If you sort of compromise a little bit, you can go down to 16-bit, 2 bytes. So 16-bit, that is considered very reasonable because the model performance doesn't get too bad, right? At 16-bit, you're using 14 billion plus 1.2 factor. So about 16 gigabytes of memory, right? Video memory. A typical model, like a video card that you can buy in the market these days, let's say that you and I can afford 4090 or 3090. How much memory does it have? 24 GB. So it means that this barely fits in for inference, isn't it? Now what happens is, so what you hope is, can I make the model work without needing fine-tuning at all? Right? If you can, then it's great. RAG is one way that you can make the model work and still get a lot of the benefits without fine-tuning. Why? Because RAG is search. And as we said, semantic search, the theory, the whole thing has been so super optimized. What is the typical search overhead? Compared to running a large language model, the search overhead is practically zero, relatively speaking. Right. For example, a large language model on your machine might be generating, let's say, 40 tokens a second or something like that, 40, 50 seconds. Oh, 40, is it per minute, per second? Local machines. No, on one of these. Okay, I keep forgetting that number. But okay, a small number. But relatively speaking, a search, because search is encoder-based, generally you can run a large volume of concurrent searches, and your searches will still return back in milliseconds, right? 10 milliseconds, 30 milliseconds, or so forth. So search is cheap. So what you're doing is you're amplifying the value of the large language model with a lot of data, which you can search from. Are we together? So that is inexpensive. Now comes the whole question, is that enough? And the best way to answer that is always, and this is a thing that you have to remember, because on the internet, you find these debates. People are saying, and I don't know how such extreme opinions come in. It's good because, the algorithms promote extreme opinions, right? Try to make a moderate statement, like all things considered, both presidential candidates have some good things and, some good things to bring to the economy if their plans are executed. Nobody will read your article, right? You take out a dagger in your writing. Bad. This guy is horrible. And it will have millions of viewership. And that's how the algorithms work. They propagate extreme opinions. It's a tragedy. So the extreme opinions in the world, that is, and very popular. The unfortunate thing is people read that and they come and keep parroting it into corporations. But one of them will say, fine-tuning is dead. Do this experiment, please. Just Google fine-tuning is dead. And see how many pundits are opinionating that fine-tuning is dead. Right? I would like you to do this and tell me, are you finding lots of great opinions with high hit rates? Fine-tuning is dead. Anybody would like to give a feedback? What is that? What are you finding? Anybody finding now, do the converse search. RAG is dead. RAG is dead.
That's also there.
That also is there. So it turns out that RAG is dead, fine-tuning is dead. Then what remains?
Everything is there.
Everything is dead. Right. So how would you explain that? What's a correct way to look at it? See guys, use RAG. Should you fine-tune? First thing with fine-tuning is this. It is the hierarchy of costs. The hierarchy of cost is this. Because you're fine-tuning, what are you doing? You're going back to this model and you're opening up the weights, isn't it? See, guys, to fine-tune, you take some data and you open up the weights. The moment you open up the weights, what is the problem that you have to face now? When you open up the weights, 3x memory, isn't it? So in the simplest form, all of these weights will have to get adjusted. So 14090, you can't do fine-tuning on 14090. Do you see that, guys? You're basically screwed. You need to up the game. That's why, by the way, in the fine-tuning course that's coming up, you'll be working on the inference server with 4 4090s. Right? So your hardware requirement goes up. To the second question, I think one of you asked, who was it? I think Virinda, you asked that, right? Data. Do we have enough data for that? So data is good news. Fine-tuning, believe it or not, you want to do with as little data as necessary. Why would you say that? Usually when you train a model, the more data is better data, isn't it? Why would you want to fine-tune a model when necessary with as little data as possible? A large language model. Hazard a guess. Why would you do that? It's like, let me put it this way. When you do a surgery, surgeons are advised to make as small a cut as possible, as necessary, right? Not to go just say, okay, let's do, we have to take out the appendix. Let's start by opening up the whole chest all the way down to the tummy. Why do we not do that? Go ahead, Sanjay.
It might kind of disturb the earlier training on the massive data.
It might disturb the earlier training. That's a very good answer. What does that mean, disturb the earlier training? Yeah.
We don't want to muck around with the weights that have already been set up, not like all of them. So we just want to carefully, wherever our data semantically matches, just change those parameters.
How would you know which ones they are?
We don't know that.
We don't know
We
that
know,
yet.
so that by feeding less data, we are just kind of ensuring only.
Minor perturbations. See, guys, you're getting close to anybody else would like to say? Go ahead, Abraham.
Fine-tuning we usually do for a very particular use case in mind. Let's say
Yes.
fine-tuning to a specific problem. So that's why you really as little data as possible because you're focusing more on that like problem.
That's right. That's right. So see, guys, the problem is these weights, they contain many things. They contain an understanding that the model has of the world, a semantic understanding. The language, when we say these are natural language understanding, the understanding is encoded in the weights. You disturb the weights too much and it begins to not understand anymore. Right? That is it. And the other more mathematical way to put it is, see, this is what happens. Suppose I have the training data, detraining, has a probability distribution. I'll just mark it out in one dimension, though it has something like this, right? And what happens is, let us say that your in-house data has a probability distribution like this. This is your probability distribution. It has to be different, isn't it? If your probability distribution was exactly the same as the training data, there was no need to fine-tune it at all, isn't it? The machine has learned this and is responding from this. right? But your in-house data is this, and you wanted to respect this. But the question is, how much, right? Because you realize that if you train it a lot on the red data, in-house data, the machine will come to only one conclusion. He says, oh my God, what I learned doesn't make sense. Let me learn just this curve, the red curve. Trouble with learning the red curve is your in-house data is a very tiny window into the reality, external world, right? And I'll illustrate this with an example in a moment. And so what will happen is a general purpose large language model will go through, the word that is used is catastrophic forgetting. It will go through catastrophic forgetting. Many places I've seen that when people are not skilled at fine-tuning, it reminds me of a Urdu phrase. Forgive me if you don't know the meaning of it. Neem Hakim Khatrai Jan. Anybody knows what that means? Translation. Okay, we should ask LLM to translate it. Yeah, Bridal, go ahead.
Which one?
Mike. Mhm.
Yeah.
Yeah. They'll arrest your health. No, basically it means that nothing so dangerous as a newly minted doctor. Right. So there's a lovely book actually written by a Berkeley doctor here, who he has written one of the most wonderful books on medicine. The title of that book is "Kill as Few Patients as Possible." Right. And he's very honest. Actually, I come from a family of medicals, so I can sort of relate to that.
Learning stage.
Yeah, every physician, trust me, is a murderer. The only question is how many people has the person killed?
That's
Right?
controversial.
Every surgeon, every physician, because that's how you learn. There's no getting away from it.
Because native language we have where they say, that means a person who kills 1,000 people is considered a half a doctor.
Right. That is right. So the point is, guys.
So Asif, quick question. So, like you mentioned that this is the data on which the large learning model has been trained on, right? And this is the data that you have,
Right.
the one in red. So, what is the technical term you would use to define your data, which is like very specific to your domain and might have some biased information about your company?
Since you want out of distribution data, your data is out of the distribution that
Out of the
represents the
distribution
training
data.
distribution, right? So now, anyway, the point that I was making about the physician is that, see, guys, all of you, I have done that. At one time when I started fine-tuning the LLMs, I've been fine-tuning models all my life, practically, throughout my career. I've been doing machine learning for many years now. My first experience with fine-tuning large language models were generally, I would be embarrassed that it did worse than it did than what I started out with, right? Fine-tuning, therefore, is like surgery. You have to be good at it. So there are two aspects to it. Hardware, which is a scarce resource. You need to have good hardware. Actually, data is not the problem. Data you usually have. There's a reason to do fine-tuning, which is your data. Your data is different from the general purpose data outside. But the thing that most people forget, the most scarce resource is a person who is not a newly minted doctor, a person who genuinely knows how to properly fine-tune a model. I think that is a pretty resounding advertisement from a fine-tuning course coming up, isn't it? Well, okay. So the point that I'm making is there's a reason, I'll quote a stat. Typical, how much does a guy who knows fine-tuning in Silicon Valley, who can demonstrate that they have experience properly fine-tuning a model. Can you guess what their typical salary is, even if they are just with 10 years industry or 7 years industry experience? Can you guess? Come again?
A million.
500,000, a million? Actually, I can tell you with confidence that they're paid close to 2.75 million. And not because they're exceptional. Not because they're exceptional. Not because they are Andrej Karpathy or somebody like that. Simply because they know how to fine-tune.
As if like right now, the 70 billion meta model, model is running out.
Yeah.
We call this in inference mode, or it is in.
Pure inference. You're in inference mode.
So are we doing like still that 70 billion model is going to be?
Are you actually fine-tuning it in your workplace?
Yeah. So suppose like I have some idea.
Yeah.
I'm still using the 70 billion data something.
70 billion
Still-
model.
Yeah, 70 billion model. So I can still, for my use case, I need to fine tune.
Yeah. Yeah. See, here's the thing. The basic rule is, and guys, I will answer this question. So why don't I come to the crux of what I was going to say? See, to fine-tune or not, is fine-tuning dead? Is to fine-tune or not? To RAG or not? Right? To do this or not? To completely train the model? Which of the fine-tuning approaches will you take? So for example, one method that avoids catastrophic forgetting is called a parameter efficient fine-tuning using LoRa. And these are technical terms we'll come across, but LoRa, low rank adaptation, are ways to prevent catastrophic forgetting. But nevertheless, what should you use? This question keeps coming up over and over again. And believe it or not, this question has been perfectly answered in this field. It has been answered actually, not just as an opinion or as an experience, but as a mathematical theorem. Right? In fact, of the field of AI, of the field of machine learning, usually you don't expect a contribution to be foundational to the theory of human knowledge itself. Right? I'm talking about the same level as Gödel's incompleteness theorem and things like that, foundational ideas. But there's one result of machine learning that is so deep, so profound, that it is a contribution to the theory of human languages, of knowledge itself, the concept of knowledge, scientific knowledge itself. It is called, you would imagine it would have a really serious name, right? Gazuba-Baguga theorem or something. Right? Some great scientist name. It is called the no-free lunch theorems. Actually, I'll put a little s because it's a group of theorems. And theorems, by the way, are born perfect. Once the Pythagoras theorem was proved, you realize that there was never a V2 version of Pythagoras theorem, but your operating system is already in its 11th version and still imperfect, right? Or whatever it is. So no free lunch theorem says something very, and guys, if you can take away something from today and remember it forever, please take this. Please take this. Only the data will tell you whether an approach is right or wrong, whether it is worth doing or not. Right? Let me couple it up with another statement by the great mathematician Box, who said, all models are wrong. All models are wrong. Let me overemphasize this, but useful, or rather, effective. What does that mean? Science is never a pursuit of the right answer. There are no right answers. Is Newton's law correct? We know it for a fact that it's not correct. Right? Why? Because Einstein's theory of relativity makes a correction to it. Right? Quantum mechanics makes a correction to it. Right? We don't know. Do we know that the Einstein's theory of relativity is correct? Special relativity is correct? No, that's not true. It turns out there's general relativity which makes a correction to special relativity. Do we know that general relativity theory is correct? No. Actually, we know it for a fact that it is not correct. Do we know that quantum mechanics is correct? Actually, we know it definitively, 100% sure that it cannot be correct. Quantum field theory cannot be correct. I say it as a person with formal training in these fields. I cannot think of a single scientific theory that is actually known to be correct. And yet we are taught these things in school books. Why are we? Because they work. In practical life, they work. They are, in other words, they are useful in solving real world problems. All theories are effective models. Remember, a theory is nothing but a model. When you build a model, the only question that you have to ask ever is not whether this model is correct or this approach is correct. There is no such thing as correct in science or in machine learning. The only thing is it useful or effective? Am I making sense, guys? So now, when you look at it through this lens, I have a model. Is fine-tuning the right thing to do? Should I fine-tune, or is fine-tuning dead? What's the right answer to that?
It depends. Depends on the data.
The data.
Yes.
Yeah.
The only way you can find out is by doing it. Do. If you can have the resources to do. But prior to that, don't have assumptions that it will work or it won't work. You don't know. You cannot know. You simply cannot know. If you don't do, you have a missed opportunity, because there might be a better model that you never ended up with because you never fine-tuned. On the other hand, having fine-tuned, you might realize that this whole thing was a waste of time. It is the nature of machine learning. There is no two ways about it, right? There are no two ways about it. Same true with RAG, with all of these things. Remember, everything at the end of it is a model. And all models are wrong, but you're in the search for effective models, and only the data will tell you after building the model whether it was a worthwhile exercise or not.
But are you not, even if you're doing a fine tuning, right, and it's been, sorry.
Yes.
Are you not, when you're fine tuning a model, and testing it? Right?
Yeah.
In order to get, if the models are, the new models are coming in, you got to do the same kind of activity, right? And you don't know whether it's going to work as the same way you did it for the old. I don't know whether this is being discussed there or not, but there is more and more discussion around it saying, you're going to spend time on one, money, effort, and everything else. Maybe make it work. And then if there is a new down the line, you got to do the whole thing again.
Yeah, see, that is where experience and a bit of black magic comes in. And that's why now you realize why people who are in this, they are not just people who are following a methodology, but who have, very much like surgery, you need a gut feeling, right? See, before, as you know, well, in India, people are scared. Most people don't do tough surgeries. In US, right? If you go to a top research place, it's a very complicated surgery. People will turn it down. A good surgical team will have a gut sense of what will go wrong and whether it is worth doing the surgery or letting the patient just live the days out. Isn't it? And that feeling, while there's a vast amount of learning and experience that informs that feeling that you get, at the end of it is a gut feeling, right? There is a subjective element to it. And my own experience is, people often ask me that, how come you succeeded? I was also trying to fine tune, mine didn't fit. How did you succeed? And the simple way to say it is that because you haven't failed 1,000 times, right? Go develop that experience, that feeling that will make you able to tell whether we should embark on this thing. See, the ones which are foolish paths, right? Experienced person will immediately tell, don't do that, right? But he won't be able to tell that if you do this, you are guaranteed to succeed. He'll just say that, yeah, this I think may work, right? That's how we are. That's how, I mean, this is the reality I'm mentioning it. If anybody says they can definitively tell you that it works, that guy is fooling you. Now, here is something nice about, and this is the whole theory of the fine tuning and so forth. It's a very involved subject now. So one of the ways you do it, for example, if you use LoRa's, two things happen. First, LoRa's are relatively quick to train, right? And they're non-destructive. Non-destructive in the sense that your initial model has not gotten screwed up. It's still there. So what you can do is they're composable. You can fine tune with this data, with this data, with this data, and you can hybridize it together. Let me make it very visual. In the field of image generation, so people have these days, image generation is a passion for the young. And they actually know more about LoRa than most engineers know. For a very practical reason. Because if you want to always insist that suppose you want to make a pretty girl, that she must always have a particular look like some particular model or actress or whatever it is. There is a LoRa adapter for that, right? What it will do is anytime you generate a female face, it will look like that. If you insist that your person must be wearing glasses, right, or have a scholarly look or something like that, right? There's a LoRa for that. If you insist that the person comes out always with black hair and not with blonde hair or something like that, or bald, there's a LoRa adapter for that. There's a LoRa adapter that will put you on a really powerful horse, riding a powerful horse, right? So what does that give you? Now you can compose all of these together effectively, right? And I'm just giving it to you. So what these young people do is they think, okay, what is the character I need? They describe it in a prompt, but at the same time, they make sure that the model that they are using to generate the image onto which they plug in these LoRa adapters. The beautiful thing is those LoRa adapters are plug and play onto the base model, right? So that kind of fine-tuning, actually, there's a reason why LoRa fine-tuning and that whole family of approaches is highly effective. And one of the most popular ways of fine-tuning. Other big benefit of LoRa is that you can do it on very minimal hardware. Actually, believe it or not, you can do LoRa adapter literally on your 4090. Because what you do is you leave the main model alone and you just take a tiny little matrix that you're training to capture the out-of-distribution nature of your data. So, I mean, there's a lot to it. Now, there are other techniques. Some people, what they will do is they'll take the whole model, but they'll unpack. They know exactly which of the weights to unfreeze, to open up, right? They will say, okay, the last few layers, let me open up. Why? Because I know that these are the higher levels of abstraction. Some others will say, no, I need to go and change the early layers for whatever reason, right? Or they will selectively open up the weights so that the initial model is not disturbed too much. Right? But at the end of the day, fine-tuning is surgery. The closest analogy I'll give you is fine-tuning is surgery. If you look at the LLM with its language understanding, it's brain surgery. You have to be careful what you're doing. Right? So then the last step of escalation is you completely train a model from scratch. That's quite easy if you have just about 25,000 GPUs lying around, right? And lots of tokens and electricity to burn. But for you and me, it's not possible, right? So we and I don't do that. The word for that is industrial capture. Only the big guys, for them, it's easy. For us, it's not. For us, it's like looking at the moon and admiring it. We'll never go there, but it's still beautiful, right? So, well, that is the whole. So I hope we can put this discussion to rest about RAG, fine-tuning, training, and so forth. So this is the reality, guys. It's a tough field. It is actually a tough field. It's very easy to get into, but very hard to do well in it, to build products properly in it. And I see that every single day, actually, because I am advising and helping a lot of companies and startups. So, all right, so I'll summarize it. Where were we? I'll summarize it by saying we learned the value of RAG, right? What does RAG do? If you look from an LLM's perspective, LLM is dated, LLM can hallucinate. It's a plausibility engine. And data, a search, information, pertinent information helps you. Even if you have very large context windows, it still helps you, right? By decreasing the token, input token count. Now, we will today, so we have had a general recap. With this recap, and in the past, we also took the prompting seriously. We learned how to take search results and feed it into the LLM which was good. But then we went into the broad topic of prompting. Prompting itself has two aspects to it. What is traditionally called prompt engineering, which is basically writing the right English text to feed into a LLM. And the second aspect of it, which is fast evolving, is prompt programming, dynamic prompting. Right? Now, I'll recap the lessons we learned last time. One was that prompting is not just cursorily writing some text on ChatGPT or cloud or whatever and expecting a result. In fact, if you remember, I mentioned that they all give you a tiny text box. They encourage you to put one-liner or two-liner there, isn't it? Because they encourage you to put only one-liner or two-liner there, we all have gotten into the habit of doing that. That is the opposite of what you should do. What should we do? Anybody would like to recall? What should we do?
You should explain what we mean, how it
Yes,
is, like,
you
frame
should
it.
do. Yes,
Look in.
COSTA, yes. Excellent. Yes, Jyoti, go ahead.
I was just mentioning COSTA Framework.
Exactly. COSTA and many such templating framework. So there are certain things you must tell. LLM, the easiest way to think of LLM is 1,000 PhDs behind a curtain, right? Or what is acting, right? LLMs are excellent actors. So when you hire an actor for a movie, what do you just say? Just go act. You don't do that. First thing the actor will ask you, what's my role? Who am I? So he'll say that, okay, you're a millionaire who has become a pauper now. What's that?
They call this screen testing.
Screen testing, that's right, yeah. So you give the actor a role, a backstory. This is what you are, right? You're a beggar. Backstory is you used to be a millionaire. You gambled it away or something like that, whatever it is. Right, and then you give it a role, you give it a goal. This is in the story, as an actor, this is what you have to play, the feelings that you have to bring forth, right? So that's pretty much what you tell an actor. And you tell how that actor is going to engage with the external environment, the other actors, and so on and so forth. How does the story play itself out? So the same thing is with LLM. I cannot emphasize enough. LLM is like 1,000 PhDs behind a curtain. You have to tell which one are you calling for, right? Are you calling for the mathematician or the poet? Do a simple experiment. Tell a LLM that you are a poet whose only training throughout life is in English literature, let's say. You have never learned mathematics or blah, 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 blah. But then ask it to write code or solve a logical puzzle. And you will see that it will actually hesitate. Right? It's I don't think, I'm not sure I can do it, but I'll give it a try. And then it will solve it. Right? On the other hand, tell it that you're a first-class lawyer. Do this, do that, whatever it is. And all of a sudden now ask it to write, to convert something into some few lines of poetry with great pathos. Right. And then you will see it hesitate the other way around. It will do it, but it will hesitate. It will just say, I'm not sure if I can do a good job. But you know, it's the same LLM, isn't it? What happened? It picked on the personality. It is an amazing actor. See, in the world of acting, you're taught that actors should be like water. They should take the shape of whatever bottle they're put in. Great actors. Right? And they should completely melt into the role. LLMs are great actors. So you should give it a role. You should give it an audience. Who is it talking to? Right? The output that it generates, who is it talking to? You must describe. Am I talking to 10-year-olds? Am I talking to PhDs? Right? You must describe that. You must give the tone. Should it be sarcastic? Should it be hilarious? Should it be compassionate? Should it be professional? Should it be, what is the level or the style in which it should respond? Should it use mathematical equations? Not use mathematical equations. Right? All of those things you can specify and give guardrails. What are guardrails? Anybody? Those things that you should not do. Put guardrails that stay in this lane. Don't depart from it, right? You put guardrails. Do not do this, do not. For example, if you're writing a chat prompt that will answer a customer's question, right, on our website, what could be a very meaningful guardrail? Don't helpfully suggest that your competitor's product is better.
2 days back, Alexa, Amazon Alexa, the people asked the question whether Trump is going to win or Harris is going to win. So the Alexa was answering, but it's because of political thing. If you ask this question to Alexa, no, it's not.
Yeah, that's right.
Yes.
Basic guardrails. Like, see, certain topics are taboo, right? Politics, religion, etc., etc. Right? They're basic taboo. In civilized societies, they should never be discussed. Right? So put those in your guardrails.
I think that's what industry would need from a BII perspective, right? When it comes to GDPRs and you got to have those rails to.
Absolutely, absolutely. And you will learn this as you go through this course. Actually, guardrails in this course, right? See, here's the thing. This course is a tour through the whole of Gen AI, but in the next course, literally tomorrow's topic at Sunday. And if you just want to, if this topic really matters to you, any one of you, I invite you to just sit through 1 or 2 sessions, whichever session that you like. So tomorrow's topic actually is guardrails. How do you engineer robust guardrails? But in your case, the little bit of guardrail that you put in your COSTA framework, the way that I taught you, is good enough for now, right? So I got you introduced to prompting. And the main lesson was prompting is more serious than you think. We went through so have a good template, use chain of thought, 0 shot, few shot prompting, give examples. Examples is always a good idea because that's in context learning. Use chain of thoughts, use reflection, use self-criticism. I told you, language models have very good critiques of their own work. They actually spot mistakes in their own work. Give it a chance to correct itself. Actually, have you noticed that recently, yesterday, the day before yesterday, this thing came out, the O1 came out, GPT-O1.
Yeah, strawberry.
Strawberry. What is strawberry? Do you think it's a fun? If you really deconstruct it in your mind, I'm sure that there's some innovation there. But broadly speaking, 99%, what is it? It is just internally, it is just doing chain of thought and planning and things. All the things that you will learn, well, in one day I could teach you only so much, but everything that I'm teaching the LLM 2 course, the advanced guys, they immediately spotted that it seems to be doing exactly what you have trained us to do, right? And it seems to be taking as much time. In fact, one of the things, you notice that on the web, there's a lot of euphoria. Oh my God, this is the best model ever, right? And in some sense it is. It's very expensive. It's taking a lot of time. When you see what it is doing and how much time it takes, you would have realized, for those of you who have been writing prompt engineering with me, many of you pointed out that your own agentic framework, repeatedly, people reached out to me. They said the agentic framework they created in the course still beats O1. It still beats O1. Right? So what are agentic frameworks? They just say that good prompting is a core part of it. There's a lot more to it. I won't go into it. So what is it? Support vector students are still beating O1, the state-of-the-art model.
One after I feed it in ChatGPT. Secondly, so I gave 0.
Come again? It gave you a?
So I gave GPT 0.
Yeah.
It got confused. It started answering. I think you are referring to a new model. Like it still has to be there.
Okay. Nice. Yeah. So guys, here's the thing. If you can do agentic reasoning with the state-of-the-art model, let's say with O1, you realize that you'll get a lot more power out of it, right? Anything. So the power is not just in the models. The power is in how you harness those models, right? And somebody here is in my agents class. Who is that? None of you. Okay. Anyway, if you were there, you would literally have seen this as an actual example that the framework that we have created still beats using a previous model, a prior model, which was actually we are using Cloud Sonnet 3.5. With Cloud Sonnet 3.5 and a good agentic framework, we beat the hell out of O1 still. That was the experience of my students. Now, it is true that if you just take in favor of O1, you can say, well, what about using your agentic reasoning with the O1 framework? Then, of course, it will beat everything else. Right? So obviously, O1 is a powerful model, but the point I'm trying to make is good reasoning, good prompting is the other half of the story. You can achieve a lot with tiny models. One of the homeworks we do is we take a tiny model, 7 billion parameter model, and we find that a 7 billion parameter model with good agentic reasoning achieves the same capability as a GPT 3.5 or a GPT 4. Right? So that's that. So anyway, that is a recap of what we did last time. I will take a break and then we'll start on the topic of today. I'm stopping the recording. And guys, we'll take a short break. Actually, it's already 12:20. How about this, guys? Can we make the lunch very short today?
Yes.
Okay.
Yes.
I'll see you guys all at 1 because we have a long day and today we'll go on till 6. So let your friends and family know that 6, which is actually 7 p.m., you'll be here till then.
So Asif, like what is the agenda for the day?
We'll start at 1 and the topics for today are hybrid search and semantic chunking and associated research paper readings.
Yeah.
Are we together? And today is the last day of text, guys. From next time, we go into vision models and multimodals. Why am I not?
How long is the break now?
Till 1 o'clock, guys, go get your lunch.
Oh, yeah, lunch break. Okay.
Oh, I am no more. Somebody has taken over.
So Asif, this is Jyoti. Quick question.
Yes, please go ahead.
So the strawberry model that's released, it's
Yes.
better than the earlier model because whatever input that we are giving, it is prompting and like whatever you taught in the last class, it is doing it behind the scenes to give it.
Yeah, that is a large part of it. A large part of it that is doing all of those things behind the scene. There is more to it. There's a little bit more. I mean, there's some advancement in research also, but that is a significant part of it.
Okay, thank you.
Okay, for some reason, guys, it's not letting, okay, streaming server.